Welcome back to the Deep Dive. We're the show that takes a whole stack of sources and, well, boils them down for you, giving you that shortcut to really knowing what's going on.
That's the goal.
And today, wow, we are plunging into a story that's it's full of intellectual battles, unexpected turns, and it fundamentally shaped, the entire landscape of artificial intelligence as we know it.
It really did.
Imagine this. A discovery happens, it's so exciting, it kicks off a whole new field. Everyone's dreaming of thinking machines, big visions.
Huge visions.
Then, bam, a brilliant, really groundbreaking critique comes along and just seems to snuff it all out. For a decade, casts this long shadow.
Yeah, an AI winter, as they call it.
Exactly. But then, and this is the wild part, that same critique, the thing that seemed like a total dead end, it turns out to be this kind of hidden blueprint, an unexpected spark for an even bigger revolution, one that's, frankly, still unfolding right now.
It's not science fiction, though it sounds like it. It's the real messy history of AI.
Yeah.
It shows you how progress, well, it rarely goes in a straight line, does it?
Yeah.
Not at all.
It's often this winding path. Sometimes it even doubles back. And these moments of really tough, rigorous criticism, even if they feel devastating at the time, sometimes they end up paving the way for huge leaps forward.
Right.
And what's really key here, I think, what we want you to take away, is how sometimes figuring out exactly what doesn't work, what the limits are, can be the most powerful way to show what is actually possible. It pushes boundaries.
Absolutely. So our mission today, take you back to the 1960s. A really vibrant time, but also, a bit turbulent for AI. We'll explore the initial promise, almost boundless promise of these early neural networks. They were called perceptrons.
Right. Frank Rosenblatt's work.
Then we'll dig into exactly why two AI giants, Marvin Minsky and Seymour Papert, dragged this bombshell critique, concluded these machines had fundamental, unfixable limitations, and that's what triggered the AI winter.
The serious setback for that whole line of research.
But here's where it gets really interesting. The irony kicks in. We'll show you how their criticisms weren't just roadblocks. They were kind of an accidental blueprint for overcoming those exact challenges, setting the stage for deep learning, the stuff we see everywhere today.
Yeah.
So you'll get a shortcut, a real understanding of this pivotal moment in AI history, often misunderstood, actually. And you'll see why sometimes saying you can't do this is the best way to figure out how you can.
Precisely. It's about seeing that shift. From this early, almost speculative phase, tons of optimism.
The romanticism, they called it.
Exactly, that romanticism, to a phase demanding real maturity, sharp criticism, understanding that back and forth, that dialectic, how critique drives evolution.
That's cute.
Not just for AI's past,
Yeah.
but for figuring out its future, too.
Definitely. And to guide us to really unpack this whole technical saga, this intellectual turning point, we've got Minsky and Papert's original 1969 work, Perceptrons.
The source itself. Essential reading, if dense.
Yeah. Plus, we've pulled in some more recent perspectives from books like AI Snake Oil, Deep Learning, and Empire of AI Dreams and Nightmares, just to give a fuller picture.
Good range of sources.
Okay, let's roll up our sleeves. Time to dive into that early promise, that initial spark. So, before the AI winter hit, back in the, let's say, the late 50s and early 60s, it was kind of like the Wild West for AI research.
Yeah, definitely pioneering spirit.
And there was this huge wave of optimism, a lot of it driven by one guy in particular, Frank Rosenblatt.
Ah, yes, Rosenblatt, Cornell, psychologist, neurobiologist, a key figure.
And he introduced this radically new idea, this new class of devices. He just called them perceptrons.
That's right. His work, building on some earlier ideas, like Hebb's learning rule, really gave us the name perceptron and a kind of tangible model for it.
So what was a perceptron at its core?
Well, they weren't physical brains, obviously. They were more like conceptual models. Minsky and Papert later called them abstract versions of machines.
Okay. Abstract machines. What were they for?
Their main goal, pretty ambitious, actually, but
Yeah.
elegant. Pattern recognition and learning. That was the dream.
Learning patterns. Okay.
Yeah, the idea was they could make decisions by adding up evidence obtained from many small experiments. Does that make sense?
Adding up evidence. Like weighing different factors.
Exactly. It felt very intuitive, very biological, almost like how we might weigh pros and cons. And even Minsky and Papert admitted, that most and perhaps all more complicated machines for making decisions share a little of this character.
So even the critics saw its foundational importance.
Oh, yeah. They knew you had to understand perceptrons, even if you were going to point out their flaws. It was seen as crucial.
Adding up evidence. Sounds simple enough, but how did they actually, like, work? What were the mechanics?
Okay, think of it as a really basic network, just a single layer.
One layer, got it.
You feed it input. Could be anything, pixels from an image, maybe financial data, whatever.
Yeah.
Each input gets a weight, just a number saying how important that input is.
Like a score. Sort of, yeah. Then the perceptron calculates a linear combination. Fancy term. But it just means multiply each input by its weight and then add all those results together. Simple summing up.
Okay, so inputs times weights, add them all up. A weighted sum.
Exactly.
But if that's all it did, wouldn't it just be linear? That doesn't sound powerful enough for complex patterns.
You nailed it. That's the crucial next step. That weighted sum isn't the final output. It gets transformed by a nonlinear activation function.
Nonlinear activation function. Okay, breaking that down.
Think of it like a switch, or maybe a dimmer. It takes that raw sum and squashes it, often to a value between, say, 0 and 1.
Like turning a volume knob into just on or off?
Kind of. A common one was the logistic sigmoid. If the sum was high, the sigmoid might output close to 1, meaning yes, or pattern detected. If the sum was low, output close to 0, meaning no, or pattern absent.
Ah, so it forces a decision. It's not just a sliding scale, it pushes it towards one category or another. Precisely. That nonlinearity is key. It lets the perceptron classify things into categories. Without it, if you tried stacking layers of these things, mathematically, it would just collapse back into a single linear layer anyway. Useless for complexity.
Gotcha. The nonlinearity is what makes it more than just fancy arithmetic. It introduces the potential for complex decision boundaries.
Exactly right. So it's about classifying patterns, shapes, letters, whatever, based on this weighted sum pushed through a nonlinear gate.
And this idea, simple but powerful, biologically inspired, it really caught on, didn't it? This was the Romanticism era Minsky and Papert mentioned.
Oh, absolutely. These weren't just tucked away in academic papers. Perceptrons were publicized, discussed widely. Magazines, newspapers. There was huge buzz, real excitement.
People thought they were on the verge of, what, thinking machines?
Pretty much. Minsky and Papert said the early days of cybernetics had this flourish of romanticism, full of attractive and exciting new ideas. There was this genuine, palpable hope for creating learning systems capable of independent thought. Like, really soon.
Independent thought. Wow.
Yeah, translating languages, complex reasoning, maybe even having conversations. The potential felt almost limitless for a while there. And the perceptron, it was a poster child for that whole optimistic vision.
And it's really important for you, listening, to get a feel for that optimism, that backdrop of huge expectations, because it helps you understand just how big a shock the critique was when it landed.
Definitely.
This seemingly simple concept held such massive promise. The bigger the dream, the harder the fall when someone points out the flaws. So with these sky-high hopes, this almost feverish excitement, the stage was set for a major reality check. And it arrived with a bang in 1969.
Yep, the year the music stopped, in a way.
That's when Marvin Minsky and Seymour Papert published Perceptrons, an introduction to computational geometry. And this wasn't just another paper, this was an intervention. Deliberate, sharp, and game-changing.
Absolutely pivotal. You have to understand who Minsky and Papert were. Giants in the field.
Yeah.
Co-founders of the MIT AI lab. Huge authorities.
Right, not just random critics.
No way. And they argued, very explicitly, that the field needed to grow up. It had reached a time for maturity. All that early speculative enterprise, that romantic flourish, it needed to be matched now by equally imaginative standards of criticism.
So time to get serious, rigorous.
Exactly. Their book was this incredibly detailed mathematical takedown of what they saw as, well, hype. Unscientific claims surrounding perceptrons. They included rather sharp criticisms of earlier work. A lot of it, they basically said, was without scientific value.
Ouch, without scientific value. That's fighting words in academia.
It really is. This wasn't a gentle nudge. It was a direct challenge, a call for, brutal honesty, mathematical self-assessment. They felt the field was seduced by easy wins and needed hardcore theory.
You can almost feel the chill going through the connectionist labs back then. Okay, so stripping away the drama, what was the core argument? What fundamental flaw did they pinpoint that was so devastating?
The absolute core was the limitation of single-layer networks. They proved mathematically that these simple perceptrons just could not solve certain types of problems. No matter how you tweak the weights, no matter how long you train them.
Couldn't solve them at all. Like, impossible.
Impossible for that architecture, yes. And the classic example, the one everyone remembers, is the parity predicate problem.
Parity. Okay, what's that in simple terms?
Imagine you have a row of lights. Some are on, some off. The parity problem is just figuring out, is there an odd number of lights currently switched on?
Okay, so 3 lights, 2 on, parity is even, 1 on, parity is odd. Simple enough. And a perceptron couldn't reliably learn that.
Couldn't learn it efficiently or reliably? No. Seems basic, right? But they showed that for a perceptron to represent parity or related things like the XOR function, exclusive OR.
XOR, where it's true only if one input is true, but not both.
Exactly. To handle XOR or parity, a perceptron would need weights, those coefficients that grow exponentially with the support size of the masks.
Whoa, okay. Exponentially. What does that mean practically?
It means the complexity explodes. To solve a slightly bigger version of the problem, you'd need astronomically bigger or more precise weights. Imagine needing, like, 1,000,000,000,000 knobs tuned perfectly just to tell if 10 lights have an odd number on. It becomes completely impractical, intractable.
So not just hard, but fundamentally broken for scaling up.
Right. And for more abstract versions, like parity on infinite sets, they showed the coefficients would have to be unbounded, meaning infinite precision, infinite capacity, mathematically impossible.
Okay, so it's a deep, baked-in limitation of that single-layer design. Not just an engineering hurdle, but a theoretical wall.
A fundamental barrier, yeah. Basically, perceptrons were great at problems that were linearly separable.
Linearly separable.
Means you could draw a single straight line or a flat plane in higher dimensions to perfectly separate the yes examples from the no examples.
Like separating apples from oranges if they're in 2 distinct clumps.
Perfect analogy.
Yeah.
But problems like parity or XOR, they're not linearly separable. You can't draw one straight line to divide the odd cases from the even cases or the XOR true cases from the false cases. They're mixed up in a way that needs a more complex, curvy boundary.
Ah, okay. So single layer, straight line decision. Parity XOR needs curves.
That's the gist. And Minsky and Papert argued these problems required multiple layers of abstraction, which a single-layer perceptron just didn't have.
Now, didn't they also argue this limitation wasn't just about single layers, that even adding more layers might not fix the core issue for certain complex problems?
That's a really critical point, and yeah, it often gets glossed over. They weren't only dissing single-layer perceptrons. They're talking about the order of a predicate, mentally. How many inputs you need to look at simultaneously to figure out the answer. Parity needs you to look at all the inputs at once. It's a high-order predicate. Their math suggested that even multi-layer networks would struggle badly with these high-order problems. They argued the order a layer could handle was limited by the previous layers, meaning the computational cost for these complex functions would still balloon, even with more layers.
So just stacking layers wasn't a magic bullet, according to their theory. The fundamental representational power was still limited for these kinds of tricky, abstract patterns.
That was their argument. They believed the architecture itself imposed limits on the types of functions you could learn efficiently. It wasn't just hard. It was potentially fundamentally inefficient or impossible for that paradigm.
Wow. Okay, so they frame this using an analogy too, right? Something about hill climbing.
Yeah, hill climbing systems. It's an analogy for optimization, trying to find the best weights by taking small steps uphill towards a better solution. They said, look, instead of just hoping hill climbing works everywhere, we need to understand the kinds of problems that create obstacles to climbing hills, like local peaks where you get stuck or flat plateaus.
Get rigorous about the problems themselves, not just the algorithm.
Exactly. Define what's computable, what's efficiently learnable, and what isn't. It was a call for deep mathematical understanding, a stark contrast to the earlier optimism.
And the impact. This wasn't just filed away in a library. This critique hit like a ton of bricks, right? Leading to the AI winter.
Oh, absolutely.
Yeah.
Minsky especially had immense stature and platform at MIT. He and Papert, with their intellectual weight, effectively quashed connectionism as a major research avenue.
Right.
For years.
Quashed it.
Well, their critique directly fueled the AI winter. Funding for neural network research just evaporated. Neural network research for a decade pretty much shut down. If you were working on this stuff, suddenly your grants were rejected, your papers questioned, careers stalled.
So the money and attention shifted elsewhere.
Completely. It swung heavily towards symbolic AI, logic, rules, knowledge bases. That became the dominant paradigm. Symbolism reigned, as one source put it.
Okay, so for you listening, this is a huge turning point. It shows how a really rigorous theoretical critique can totally redirect a scientific field. Funding, research, careers, all impacted for a decade or more. It's the power of critical thinking, even if it felt destructive at the time.
Yeah, it closed the door very firmly. But ironically, as we'll see, it also kind of pointed unintentionally towards where the next door was. The limits they defined, they became the obstacles to overcome.
It's just fascinating how history works, isn't it? This critique that seems so final, so devastating, turns out it was also carrying the seeds of the comeback.
Hidden in plain sight almost.
Because even during that AI winter, when Minsky and Papert's book held sway, the connectionist dream didn't completely die out.
No, it flickered on. There was this small band of connectionists who just held fast to Rosenblatt's pursuit. They kept plugging away, often quietly, against the mainstream.
Persistent folks.
Absolutely. And one of the key figures in this underground movement, let's call it, was Geoffrey Hinton.
Ah, Hinton, a name many will recognize today.
Right. He, along with people like David Rumelhart and Ronald Williams, made a key improvement to early neural networks back in the 1980s, while symbolism still reigned.
And there's a direct line from him to today's AI, right?
Yeah, get this. Hinton later became the PhD advisor for Ilya Sutskever.
One of the OpenAI co-founders.
Yeah, exactly. A clear intellectual lineage right there. From that quiet persistence in the 80s, straight to the heart of the current AI boom. These were the intellectual grandparents, you could say.
That's incredible. Shows how ideas can simmer for decades. Okay, so what was this key improvement that Hinton and his colleagues came up with? How did it tackle the Minsky and Papert limitations head-on?
Well, it directly addressed that core critique, the need for multiple layers of abstraction and the whole order-limited predicates problem. These connectionists, they looked at why the early networks failed and basically hypothesized that their neural networks were failing because they were too simple.
Too simple meaning, just that single layer.
Exactly. They realized to better mimic the human brain, the software likely needed multiple stacked and connected layers to form what they eventually called a deep neural network.
Deep, as in multiple layers deep, creating those layers of abstraction that the simple perceptrons lacked.
Precisely. Remember the XOR problem. Can't solve it with one straight line. But the intuition was maybe if you add hidden layers, those layers could learn to transform the input data, warp it, bend it.
Into a new representation where it becomes linearly separable, like folding the paper.
That's a great way to put it. The hidden layers, especially with their nonlinear activations, could learn to map the inputs into a higher dimensional space where a simple linear separation is possible. It's like the network learns to re-represent the problem in a way that makes it easier to solve at the next level.
So the depth, the multiple layers plus the nonlinearity, that gave it the representational power Minsky and Papert said was missing.
It provided the potential for that power, yes. But there was still a huge problem. How do you actually train these deep networks? It was notoriously hard. The credit assignment problem, they called it.
Right. If the final output is wrong, how do you figure out which of the maybe millions of weights buried deep in the hidden layers was responsible? Who gets the blame or the credit?
Exactly. And that's where the real breakthrough came. Backpropagation.
Backpropagation. Okay, this sounds important.
It was the engine. Hinton and his co-authors didn't necessarily invent it from scratch, but they developed and really showed how to apply it effectively to these multi-layer networks. It made deep learning practical. It allowed these networks to exchange and process information across their layers in a way that actually solved that credit assignment puzzle.
Okay, can you walk us through backpropagation? How does it work sort of intuitively? Sounds like the magic ingredient.
Right. Think of it like this. The network makes a prediction. It's wrong. You calculate the error. How far off was it?
Okay.
Backpropagation then takes that error signal and sends it backward through the network, layer by layer, from output back towards the input.
Propagating the error back, hence the name.
Exactly. And as it goes back, it uses calculus, specifically the chain rule, to figure out how much each individual weight contributed to that final error. It calculates a gradient for each weight.
A gradient.
Right.
Like the slope of the error.
Yeah.
Showing which way to adjust the weight to reduce the error.
Precisely. It tells you, for this specific weight, if I increase it slightly, will the error go up or down? Based on that gradient, you tweak the weight just a tiny amount, nudge it in the direction that should reduce the error next time.
So it's like a massive coordinated game of hot or cold for every single connection in the network.
That's a good analogy. And you do this over and over again, millions, billions of times with tons of training examples. The network gradually adjusts all its weights, minimizing the overall error it learns. Technically, it's a form of gradient descent, specifically stochastic gradient descent, when done with batches of data. And backpropagation is the efficient way to calculate those gradients in a deep network.
Wow. Okay. So multi-layer architecture gives the potential, backpropagation provides the learning mechanism, and this whole powerful combo got a catchy name.
It did. As the power of these deep backpropagation trained networks started becoming clear, especially in the 2000s, Hinton cleverly gave this multi-layer processing the name deep learning.
Deep learning. And the deep explicitly refers to those multiple layers, the solution to the original perceptron's flatness.
Exactly. It was brilliant branding, really. Captured the essence of what made these networks different and powerful. Learning deep representations.
It's kind of mind-blowing that this one core algorithm, gradient descent, enabled by backpropagation, is underneath so much of modern AI.
It truly is remarkable. You look across the field today, and researchers use a single algorithm across the board with minor variations, and that algorithm is gradient descent.
The same algorithm for chatbots, image generators, medical diagnosis?
Pretty much. It's incredibly empowering. Think about it. The same learning algorithms behind chatbots, text-to-image generators, and thousands of other AI apps that perform varied functions. It's like a universal learning engine.
That seems almost too simple. How can one algorithm do all that?
Well, the core learning mechanism is the same. Adjust parameters to minimize error based on gradients. But what differs is the training data and the architecture.
Ah, okay. So different data, different network structures, but the same learning rule.
Exactly. You feed text to a transformer architecture for a chatbot. You feed images to a convolutional network for object recognition. The structure is optimized for the data type. But how the weights in that structure get tuned, that's gradient descent via backpropagation. This universality is a huge reason AI has progressed so fast recently. Breakthroughs in one area often transfer.
Okay, this is definitely an aha moment for you, Lee.
Yeah.
Minsky and Papert's critique, the thing that caused the AI winter, it pinpointed the exact architectural weakness, the single layer, the inability to handle nonlinear abstraction, the high-order predicate problem, and overcoming that specific limitation with multiple layers and backpropagation is what unleashed deep learning.
Yeah, their what cannot be done became the roadmap for what needed to be done. Even if they didn't intend it that way at all, it was a map waiting for the right tools backpropagation to unlock it.
So the dam breaks. After the AI winter thaw, after the persistence of Hinton and others, after backpropagation unlocks multi-layer learning, deep learning explodes. And the capabilities just start soaring past anything imaginable in the perceptron era.
Totally. It's not just incremental improvement. It's a qualitative leap. These systems started solving problems that were fundamentally impossible for the original perceptrons.
Like those complex classification tasks you mentioned, perceptrons struggled with anything nonlinear, but deep learning.
Deep learning excels at them, specifying which of K categories an input belongs to, whether K is 2, like cat versus dog, or thousands, like different types of objects. These networks learn those complex, curvy decision boundaries needed for real-world data. They effectively solved the linear separability problem that stumped early perceptrons.
And we see the results everywhere now, things that were pure science fiction just decades ago. Object recognition, for instance. A perceptron couldn't reliably do parity.
Right. And now, modern object recognition is best accomplished with deep learning. It's staggering. Think about robots like the Willow Garage PR2 that could recognize different kinds of drinks and deliver them. That needs sophisticated vision.
Or just tagging faces in your photos automatically. That's deep learning.
Absolutely. That same core tech enables recognizing faces, objects in self-driving cars, identifying anomalies in medical scans like X-rays or MRIs. These systems process huge amounts of visual data, learning hierarchies of features, from simple edges to textures to parts of objects to whole objects. It's layers upon layers of abstraction, exactly what Minsky and Papert said was needed, but achieved in a way they likely didn't foresee.
It's not just seeing pixels, it's building up a representation. And it's not just vision, right? Natural language took a massive leap, too.
Huge leap. We went from brittle, rule-based systems to incredibly flexible neural networks. The success extends powerfully to chatbots, the ones that can actually hold a somewhat coherent conversation.
Somewhat coherent being the operative word sometimes.
Tuckles, fair enough. But also things like text-image generators, DALL-E, Midjourney. You type words, get a picture. That required a deep, abstract understanding of language and visual concepts.
Yeah, the ability to connect astronaut riding a horse to actual pixels in a specific style. That's profound.
It really is. It shows this capacity for handling highly abstract, nonlinear patterns in language and concepts, generating contextually relevant text, translating languages fluently. It's a direct demonstration of mastering those multiple layers of abstraction.
And underpinning these capabilities are ever more complex network designs, right? It's not just stacking identical layers anymore. The architectures themselves have evolved.
Oh, dramatically. The basic feed-forward structure, successive layers, connections running from every unit in one layer to every unit in the next, is still fundamental, but we've gone way beyond that.
Like what?
We'll take LSTM recurrent networks, long short-term memory networks. These are designed for sequential data, like text or speech.
Recurrent, meaning they have loops.
Feedback. Exactly. They have self-loops and these special gating units that control the flow of information. It's not just data flowing straight through.
Gating units, like little traffic controllers inside the network.
That's a great way to think of it. LSTMs have internal memory cells. The gates decide what information from the past to remember, what to forget, and what new information to let in.
Ah, so they can handle context over time, like remembering the subject of a sentence from way back at the beginning.
Precisely. That's crucial for handling long-term dependencies in language. Without that, the network would have the memory of a goldfish. So yeah, the broad pattern of connections, the architecture itself, it's now a massive part of the design process. Choosing the right architecture, convolutional, recurrent, transformer, etc., is just as important as the training data. It's a whole field of research in itself.
And what's maybe most mind-bending is that this isn't just about getting better at recognizing cats or translating French. There's a deeper goal, right? Something about representation learning.
This is where it gets really profound, I think. Far beyond the original perceptron scope. The goal of representation learning isn't just to classify, but to understand the underlying structure of the data.
Understand the structure. How so?
Well, a key idea, a central hypothesis, is that a really good representation should correspond to the underlying causes of the observed data. And crucially, it should represent these causes separately. It should disentangle the causes from one another.
Disentangle causes. Okay, give me an example.
Think of an image of a face. The underlying causes are things like identity, expression, lighting direction, head pose, maybe glasses or not. A good deep learning model shouldn't just learn, that's Bob smiling. It should ideally learn separate internal features for bobness, smilingness, lit from leftness, etc.
So it's not just recognizing the whole pattern, but decomposing it into its fundamental independent factors, like understanding the ingredients, not just the cake.
Exactly. And if you can do that, your model becomes much more robust and flexible.
Yeah.
You can maybe change the lighting on Bob's face or make him frown instead of smile because you've disentangled those factors.
That sounds like it's moving towards genuine understanding, maybe even reasoning.
That's the hope. Top researchers like Yoshua Bengio emphasize this, need to understand causal relationships and improve unsupervised learning without labeled examples to get to the next level of AI. It's about moving beyond correlation to causation.
Wow.
It's a massive leap from just drawing a line to separate points like the perceptron did. It suggests modern AI is just starting, to build internal models that reflect the actual structure of the world.
Okay, so for you listening, that's the deeper aha moment about modern AI. It's not just classification on steroids. It's about learning these disentangled representations, potentially getting at the underlying causes of data. That ability to handle abstraction and structure is what truly buries the limitations of the original perceptron. It's a whole different ballgame. Hashtag how'd outro. What a ride. We've covered a lot of ground here from those early heady days of the perceptron.
Full of that romanticism and promise.
Simple single-layer networks dreaming of pattern recognition, only to be met by that incredibly sharp, rigorous critique from Minsky and Papert.
Yeah, their 1969 book basically proved these simple networks couldn't handle nonlinear problems like parity. Couldn't classify things unless they were linearly separable, a fundamental limit.
Which slammed the brakes on, leading to the AI winter. Funding dried up, research shifted heavily to symbolic AI for a good decade or more. Neural nets were out in the cold.
That critique, that definition of the limits, wasn't the end of the story. It inadvertently set the stage.
Right. The AI winter eventually thawed, thanks to persistent folks like Hinton who understood the need for depth, those multiple stacked and connected layers.
And the crucial missing piece arrived: backpropagation. That algorithm, a form of gradient descent, finally gave these deep networks a way to learn effectively, to solve that tricky credit assignment problem.
Allowing them to adjust all those connections layer by layer based on errors. And suddenly, deep learning was born.
Unleashing capabilities that just blew past the original perceptron's limits. on class classification, object recognition, sophisticated language understanding with chatbots, even generating images from text.
All built on increasingly clever architectures, like LSTMs, designed to handle complex data structures and dependencies, moving beyond just pattern matching towards maybe, just maybe, learning the underlying causal structure of the data itself.
And the central irony, the big lesson here, is just striking. Minsky and Papert's work didn't kill neural nets. It forced them to evolve. Their meticulous what can't be done showed everyone else what needed to be done.
Progress wasn't linear. It was this dialectic, critique-driving innovation. An amazing lesson for any scientific field, really.
Absolutely. Understanding your limits is often the first step to transcending them.
So as we wrap up, here's that final provocative thought for you to chew on. Today's deep learning models. They're amazing, yes, but they have their own limits.
Oh, definitely. They need tons of data. They struggle with true causal reasoning. They can be brittle, lack common sense.
Right. So what are the unsolvable problems today? What are the modern equivalents of the parity problem, the things current deep learning fundamentally struggles with? What hidden, unbounded coefficients or architectural roadblocks are we maybe overlooking right now? Is there another Minsky and Papert out there getting ready to publish a critique that forces the next big leap? What will that look like?
It's the multi-billion-dollar question, isn't it? Will the next revolution come from overcoming another specific mathematical limit, leading to radically new architectures? Or maybe it'll be a completely different approach to learning, something beyond gradient descent altogether.
History suggests, as you said, the answers often lie where rigorous critique meets persistent ingenuity.
Exactly.
A fascinating question to ponder. Well, that's our deep dive for today. Thanks for joining us as we explored this incredible history of AI's ups and downs, its critiques and comebacks,
Hope you feel a bit more informed.
and maybe a bit more curious about where these learning machines are headed next.